Let's go ahead and do another two-part one. Number 8. A brick falls freely from a scaffold. What is its initial velocity? What is its final velocity after 4 seconds, and how far does the brick fall during the first 4 seconds? Okay, so here we go. We have a scaffold and a brick falling down. Okay, brick falling down, that's all it is. Okay, we don't know how high up it is. We're going to solve for how high up it is, and in this case we're just going to call that x. I know it's technically a y, it's much more like a y, but you know, we're going to deal with it anyway. Okay, all right, so let's go ahead and get started. For a, we want to know how fast is it moving, v final at t equals 4 seconds. Okay, there we go. And then for b, we want to know what is its change in x after 4 seconds at t equals 4 seconds. So we don't actually need to change much of our numbers while we're doing our thing. But let's go ahead and get started. So, hey, well, thank you, the Mexican kid. Do you have a first name so I can address you by your first name? Or either way, this works. So we can look back at our equation from last time that our delta v is equal to acceleration multiplied by how long we are accelerating for that period of time. Okay, and that's fantastic. And let's go ahead and substitute in that other thing we talked about. Vf minus initial velocity is equal to our acceleration multiplied by our time. Now, one of the things that we use as sort of a shorthand is we say things are dropped, we say things start from rest, whatever. These are to indicate that the initial velocity is 0. We can go ahead and write that down. That's another important thing to write down, especially if you're making that assumption, okay? Because your teachers, and especially if you're not one of my students, but your teachers can't read your minds, okay? And if you write down assumptions you're making, like your initial velocity is 0, even if that happens to be incorrect, that is still something your teacher can know and then possibly give you partial credit for. Either way, so we have an initial velocity of 0, so we can go ahead and strike that off. Now, it's falling, and it appears as though we have not been given an acceleration to work from. But it's reasonable also to assume that we are on Earth for this example, and as a result, our acceleration is just that which is the acceleration due to gravity on Earth, or negative 9.8 meters per second squared. Okay, that is reasonable to assume. So we can now plug in almost everything we've got. Let's see if we know enough to solve this equation. So we're solving for Vf. We don't know that yet, but we do have our acceleration, which is negative 9.8 meters per second squared, and we know we are falling for 4 seconds. Okay, this s cancels out one of those s's, and we end up with negative 39.2 meters per second. Now, what does that negative mean? That negative just means that we are falling in what we have decided is the negative direction. Now, down is usually indicated as a negative direction, but it doesn't have to be. Down can be positive, up can be negative, all that's fine. The only important thing is that you keep it consistent throughout the problem. That's the only thing that's important. Okay, as long as down is always negative, that's fine. If down was always positive, that would work too. But now we've solved for this now, so negative 39.2, and then let's go ahead and do part B, which is find out how far it has fallen. Now, the equation for this part is a little more complicated for calculus reasons, but it's still pretty easy to solve. Now, the equation we use for this one is as follows. Okay, now that looks like a whole bunch of nonsense to some of you, but it'll be okay. I'll explain it a little bit if you want, a more in-depth explanation, then we certainly can, but it's not completely necessary. So again, how far we go is equal to this symbol right here means our initial velocity multiplied by however long the total thing is moving, plus 1/2 the acceleration multiplied by time squared. Okay. Now this is going to work out pretty easy because, again, from some of the things that we started off with, we can reasonably assume that the initial velocity is 0 again. And anything times 0 means this entire term just disappears. Now, that will leave us with just this one. And even though that one can look a little scary, it's still pretty easy to figure out. Okay, so we have 1/2 multiplied by negative 9.8 meters per second squared multiplied by our 4 seconds squared. Okay, so this second squared right here will cancel out this second squared and leave us with meters. But let's go ahead and crunch those numbers in our calculator. So we have 0.5 times negative 9.8 times 4 times 4. So we have negative 78.4. meters. Okay, now that is the solution for our problem, but let's go ahead and again examine what it means. Okay, so what it means is that any object that fell for 4 seconds from rest would fall up to 78.4 meters. It could never fall any further than that. It cannot fall faster than the acceleration due to gravity, at least not on Earth. It might get held up in the real world for something like air resistance or something like that, but it would not fall any further, okay? And really would just about fall that far. And that seems like a really long way because it's like 200 feet. But when was the last time anything you know actually fell for an entire 4 seconds? That's actually very, very long. So there we go. All right.